the explanation of this first. Okay, so what I've got here, and I think we spent a little bit of time at the end yesterday mentioning this, but what we have going on here is a angle measurement, okay, 60 degrees, and I have taken GeoGebra here. If you look right there, okay, it says A and then times pi over 180, right? A being the 60 degrees. So here in this R value, I've gotten GeoGebra through algebra, through our formula, through our conversion facts, to change degrees into a radian. Does that make sense? Okay. Now what I want to do is actually look and ask it to find radians by their definition. Okay? Because that was finding the radians through our relationship of pi over 180, right? I want to find radians now by the definition, which is essentially really the same thing, but you're going to see it's a little bit different comparison of parts here. By definition, we took a radius, okay, and we laid it out on the circle and wrapped it around the circle how many times, right? 2 pi times, right? So basically what that says then, okay, is if I take my radius, or sorry, my arc length, and I compare it to my radius through division, okay? So take my arc length, compare it to my radius through division, I should get a radian. That makes sense? Or it should equal the radian for that angle. So what I'm going to do here is I'm going to take arc, which I've got listed here as, it's the S value. That's what arc length is, right? Okay, so I've labeled it as S. And I'm going to divide it then by my radius, and right here, F is my radius, okay? So now here's my question, okay? If I'm doing this, thanks. If I'm doing this, this is a dimension. This is a distance, right? So it might be feet, it might be inches, it might be miles, it might be whatever unit you want to. But that red arc then would be the same unit, right? Yeah. So when I go S over F, or arc length divided by radius in this case, it's going to be feet divided by feet. It might be miles divided by miles, or whatever divided by whatever as a distance, right? What happens to those through that division? Cancel out. They cancel out, okay? Now, there's going to be a value that, it's going to be called B here, that shows up, okay? Which is going to be our, actually, let me see if I can redefine it as R1, okay? So hopefully this number shows up as R1, which is going to be R standing for radian, okay? Does that make sense? I hit enter. Does it end up being the same as R was when I did pi divided by 180? Or my angle divided by 180. So now as I change the angle, okay, the arc changes, the radius stays the same, but when I take that number divided by that number, it still gives me that many radians. Does that make sense, everybody? Okay. So when we're dealing with this, okay, when we talk about radians, radians are generated by a distance divided by a distance. Okay? Therefore, they're dimensionless. They cancel out. So, but I don't want to just say 2.0944. Okay? I want you to know what that 2.0944 represents. Does that make sense? So that's why we attach the letters RAD to that 2.0944. However, what I want you to understand is that when we do calculations inside some formulas, radians are dimensionless. They disappear. Does that make sense? They don't contribute to the final answer. Okay? There will be a situation where they do, but I think it'll make sense why they do. Okay? And we'll talk about that here in a little bit. Does that make sense, everybody? Yep. So that's why I want people to act, because we're going to do some, you see on the whiteboard up there, we've got some converting, some dimensional analysis that we're going to do. I want to make sure that people understand, well, why doesn't radians cancel out? Or why don't I have to divide by radians on the bottom or something like that? And the reason the answer to that is because they're dimensionless. They don't really belong there anyway. Okay? So we got two things we got to talk about. One of them being linear speed, the other one being angular speed. Okay? They are related to one another. Okay? But linear speed is how fast something is moving in a Line, okay? So you already know this. You've been working on this since like the 6th and 7th grade, okay? Linear speed, okay, comes from this formula. Distance equals, what's distance equal to?
X.
R
Squared.
times T.
Yep.
Distance equals rate times time, right?
Yep.
Okay. Well, if I'm looking for a speed, sometimes they use the word velocity, and I'd be cautious of that because velocity has a direction as well. Okay. Speed is just a scalar. Velocity is that scalar, but then a direction that is attached to it. So velocity is actually a vector. Okay, if you guys have any of that physics background. But if I want to find R, which is a rate, which is a speed, right? These are all synonyms, kind of. Then isn't R equal to distance divided by time? Okay, so you know that. You've known that since, like I said, 7th or 8th grade, right? Okay, that's linear speed.
Wait, both of them are
okay. That rate equals distance divided by time is linear speed. Now, the only difference here is we're going to redefine some variables. Okay, because we're working here in what we call circular motion. A lot of times we don't use R. We use the letter. Does anyone know from physics? What letter you use for linear speed?
Give us a hand. Is it in the alphabet?
V. You guys use W in physics? Okay.
I don't know what
That's right. All right, so linear speed, we use that V. Okay. Equals S over T. Well, that's not D over T like it was previously, right? But we changed our rate, R, to a V. D now becomes S. Well, why is it S? Well, think about what we're talking about. We're talking about circular motion, right? Circular motion. We're talking about this situation here on the right. We're talking about how fast that blue point is moving. Huh?
Why do you have a hand there?
So the idea is that yesterday I was spinning that mouse around in a circle, right? Okay. So that that orange thing is like a rope, okay, or a chain or whatever, and the point then is the object that's moving. Okay. Now, okay, if I'm interested in figuring out the linear speed of that blue point, how fast that blue point is moving, if we were to transfer its motion into a straight line, does that make sense, everybody?
Yes.
Okay. So my hope is that we understand I'm not covering any new distance here, right? This is cyclical, it's always coming back to where it started with, okay? But if I was to transfer that distance or that speed into a straight line, we'd be called that thing linear velocity, okay? So here's the idea. If I start, get back to the beginning here. If I start right there, okay, and then I let a time elapse and I stop it right there, okay? And I want to figure out how fast it took for that blue dot to move from the red dot to where it's at right now. I need to know the time that it took, right? So I don't know, maybe that was like 0.45 seconds or something like that, whatever, okay? Some time interval. And then don't I need to know the distance that it traveled?
Yeah.
Well, the distance that thing just traveled would be,
We put it in rad or degree?
we won't talk about it. That distance that it just traveled would have been that pink distance right there, right? Is that a portion of my circle circumference?
No.
What do you call a portion of your circle circumference?
S.
Why do you call it S? What's S represent? An arc length, okay? So our D value, so if it's rate equals D divided by T, D is distance. Distance traveled, right? Well, in circular motion, that distance traveled is the arc length. Okay? So that's why we use S. That's why we rename it that way. So our formula for linear speed is equal to S divided by T. But I want you guys to understand that is still R equals D divided by T. Okay there, everyone? Okay. Another way of kind of maybe visualizing what's going on there, okay? You're gonna see questions like this. Okay, so all this is I've got a tire or a wheel, whatever, and I'm going to rotate that. But I'm gonna say that I've got a nail in my wheel, okay? Or I put like I've taken maybe this is kind of what your wheel does when you're trying to figure out when your car is trying to figure out how fast you're traveling. I'm gonna put a marker, like maybe I take a chalk line and I put it on the tire, okay? And then I start my car and it starts to move in a circle, right? Okay, and I start driving. I want to know how fast is that nail or that chalk line moving in a linear distance, okay, or a linear motion. So here's the idea. If I spin this tire, okay, is that tire in one revolution, it's going to lay the circumference out on the ground, correct? Does that make sense? Okay. Well, the speed in which that red dot is moving right there, okay, would be the linear velocity of that nail or whatever, or that piece of chalk, or that chalk line. Does it make sense? Okay. So when we, let's say, now I'm not going to be able to keep these things going at the same pace, but the idea that that line, or sorry, that point right there is moving at the same rate then that this blue one would be moving in a linear fashion. Does that make sense, everybody?
Yeah.
Okay. So they're moving at the same speed there. Okay. Questions on that, kind of the physics of that, or trying to understand that? Does that make sense?
Yeah.
Okay. And the idea is that, linear speed is when we are looking at a thing moving in a circular path, it is moving at a velocity, right? Okay. We just then need to maybe put that in, because we're not gaining ground, but put it into a linear direction. We can understand how fast that object's moving. All right. The next one is what we call angular velocity. Okay. And think about this. It's still a speed, and I from time to time will jump back and forth between angular speed or angular velocity. Angular speed is what I'm trying to say here. So let's start with this real quick. When we say linear velocity, linear speed is just the number. So let's say that I'm rotating this thing, let's say like 19 miles per hour. Okay, so 19 miles per hour would be a scalar. Does that make sense? Okay, because I have no direction with it. Okay, but this thing's moving at 19 miles per hour. When it gets to here, okay, the velocity vector would be that it's moving kind of downward that way. Does that make sense? But in this instance, now it's moving down that way. Okay, so as this thing's moving around, the direction of that speed is different at each kind of second or each instant. Does that make sense? Okay, so that's why sometimes we refer to it as velocity, because it's got a direction. Okay? And that direction then would we'd probably determine that using some tangent lines and so forth. Okay, but we don't really need to worry about that if we're going to do these problems. It's not a big deal to mess those, to transition the word speed to velocity or velocity to speed. But angular speed. Okay, again. When it's a speed is a rate, correct?
Yep.
It's a rate. So you're going to divide two things and units will not cancel out. Okay, that's what the definition of rate is. Okay, it's the comparison of two things where units do not cancel. Okay? In this case, angular speed is how fast, when I'm rotating that object in a circular path, how fast is the angle changing? Okay, per a time unit. So we see here this concept right here. Okay, so when I go back here, okay, right now I have my terminal ray and my initial ray are on top of each other. This is right before I start spinning this object in a circular motion. Okay, once I start moving this, an angle is created. Once I move the terminal ray away from the initial ray, an angle is formed. That angle right there, right? Okay. Now, however long it took for that blue point with, you see the red tangent line there, right? That red arrow, okay? however long it took that blue point to get to where it's at, okay, would be my time, right? Whatever that angle is now would be my theta. If I take my theta divided by the time, I can tell then how fast that angle took to grow to what it is. Does that make sense? Okay, so let's do this. Let's say, let's just count how many times, you guys count how many times this thing goes around, how many revolutions we do. And I'm gonna count a time. No, you don't have to count out loud. If you want to, you can. Okay? So I'm just gonna go like 1 Mississippi, 2 Mississippi, that kind of thing. Okay, and we'll talk about what our numbers mean to us in a moment. Okay, so 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi, 11 Mississippi, 12 Mississippi, 13 Mississippi, 14 Mississippi, 15 Mississippi, 17 Mississippi, 18 Mississippi, 19 Mississippi, 20 Mississippi, 21 Mississippi. Okay, so you got 5, right? 5 revolutions. I had 21 Mississippi. Okay, so you had 5 revolutions, right? So how many radians were traced out in those 5 revolutions?
Close as 10.
How many radians? Cole would be right. Close. That would be 2 pi radians one time, right?
Yep.
So if 2 pi radians is 1 revolution, you had 5 of them.
10 pi.
So 10 pi radians. Does that make sense, everybody? If it was degrees, it'd be 5 times 360, correct? Okay. So we've got 10 pi radians being that was the angle that got rotated. Okay. Took us 21 Mississippis to do it, 21 seconds. If I take 10 pi divided by 21 seconds, I now have the rate in which that angle was changing. Does that make sense? And that's called the angular speed. Okay.
What if it doesn't go full revolution?
Okay, so if it goes from there to there, right?
Yeah.
So you did how much of 1 revolution? Approximately. Half, right? So would you take 2 pi times a half? And you now get pi revolutions. Pi revolutions divided by the time that it took to do that.
But so you guesstimate?
Well, I mean, they're going to tell us.
Promise?
Yeah. All right, so angular speed is referred to as, we use the lowercase letter omega. The other day I wrote, and I was wrong, I gave you guys this list. I don't know if we talked about this yesterday.
Wait, so that's not W?
No. The other day I gave you the, we were talking about these things here. This is the Greek alphabet, okay? I wrote phi when I did, I don't know what I was thinking, but I wrote phi, which lowercase phi is kind of like that, okay?
What's an I?
Omega is that, okay? It's a little bit of a W, but there's a little loop there in the middle that kind of makes it differentiated from a W.
I thought you said you were going to give us that.
Huh?
You said you were going to print that out for us.
Yeah, I'll get to you. It's not pertinent information right now. It's not pressing information. Okay, so those are our formulas. Okay, what we need to remember. Okay, so those are the formulas that I'll provide those for you on tests and quizzes. You need to know what theta is. Theta is going to be something that you have to calculate every single problem. Okay, theta is 2 pi because 2 pi is 1 complete revolution, right?
Yes.
Times then how many revolutions you have. 2 pi times the number of revolutions. So you're saying, what if it's only half a revolution? What's 2 pi times half a revolution? What if it's 3/5 revolution? It's 2 pi times 3/5, right? If it's 1,004 revolutions, it's 2 pi times 1,004. Okay? Your vehicles do this. Okay? When you guys floor your accelerator and your RPMs go up, right? Okay? That's revolutions per minute. Okay? Of the components of your engine. Okay? So there's a link between these things. Okay? Do they both involve theta? Is theta in both those formulas? And that might be a trick question.
No.
Because when I look at it directly, theta only shows up.
But it is.
Where is it in linear speed?
S.
It's in S. Okay, so here's the relationship. If I write linear speed as this. R theta over t, because that's what S is, right? S is your radius times theta, okay? If I take this formula here and solve it for theta, I get omega times t equals theta, right? Can I plug that in for that theta right there?
Yes.
Okay, so I get R times omega times t over t. What happens?
T's cancel out.
And I get R
W.
times omega. Okay, so we've got a couple formulas here for linear speed. Okay, you can either use linear speed is equal to arc length divided by t, or linear speed is equal to your radius times omega. Those are both linear speed relationships or equations.
What if we forget what I'm taking?
Huh? Don't forget.
I don't remember.
It's the angle divided by time. Okay? It's the rate in which the angle changes. All right, so I want to do a couple examples here with you. We talked about this yesterday. I mentioned it. When we see these questions, guys, they're going to have different context to them, meaning there's different stories. This boy's rotating a stone on a sling. You guys know, like a slingshot, like not a slingshot like this, but a sling like made out of like a leather strap, and you put a rock in the middle, and you fold it in half, and you swing it, and then you let go on one end of it.
Oh, yeah.
Okay. So David and Goliath type slingshot. That's what we're talking about. Okay. You can talk about bike tires. You can talk about car tires. You can talk about Ferris wheels. You can talk about the blades on or the tooth of a blade on a saw. Okay.
Going down a hill.
Cookies rolling down a hill. You'll probably see that one the most. But whatever, you're going to see rotations of things. You might see planets in orbit. Okay. However, understand that our planetary orbit circular?
Nope.
Not exactly. Okay. More elliptical, aren't they? Oblong. Yeah. So a boy rotates a stone in a 3-foot sling. So just kind of give you the picture here. Got a rope. It's 3 feet long. Boy's holding it right there. There's my stone.
How big's the boy?
Okay. It's a boy, so probably your size.
Oh wait, how heavy is the stone?
It doesn't matter. Okay. He is spinning this. You didn't get my joke that you're a boy, not a man.
I'm not gonna say what I was gonna say. So I'm gonna let you in this.
So he's rotating this. He's rotating that at 15 revolutions for every 10 seconds. So in a 10-second time period, that thing has gone from where it is now back to itself 15 times. Okay?
That's fast.
Okay. So if I want to find the linear and angular velocities, I want to do these right now just with the direct formulas of linear velocity is S over t, and then I want to do omega, which is angular velocity, as theta over t. We'll find those, and then we'll make sure that this formula makes sense as well. Okay. When we do it, so this formula, and it's just done for convenience sake, but when that formula is provided with S has to be found by R theta, right?
Yes.
Okay, so it's kind of a formula inside a formula there. What's your R in this case?
3.
3. Now I'm going to write my units here just to prove a point, but 3 feet. Okay, now theta, remember theta is revolutions times 2 pi. Number of revolutions times 2 pi. How many revolutions take place here?
15.
15. Okay, so 15 times 2 pi would be
30 pi.
30 pi.
30
Okay, so theta, remember, 15 times 2 pi in this case. Okay, so now that should all be over time, right? Okay, now this 30 pi would have been in radians. Okay, whenever we're talking about an angle measurement with pi, it's radians. Okay, so 3 feet times 30 pi radians all over a time. What's the time duration that's happening here?
10 seconds.
10 seconds. Okay. Now, if that's my formula, how does that 10/30 work?
3,
Cancel out there, right?
0,
So now I've got 3 times 3, which is
9,
9, times this pi.
pi,
I've got feet radians, right? Up top. Over seconds on the bottom, right?
yes,
Okay. 1 second on the bottom because the 10 canceled. So, here's my question. It's a speed, correct? It's a linear speed. You're most comfortable with like miles per hour, feet per second, feet per hour, feet per minute, miles per minute, that kind of thing, right?
yep,
Have you ever read a speed that said feet radians per second?
no.
No. Why?
It's not a thing.
Radians is not a dimension. It doesn't belong there when we're talking about rates in this situation. So we get rid of that radian, and there is our linear speed. Okay? Now, the question to me is, does that, 9 pi feet per second, I'm not comfortable with that. I don't know. I always like to put things in units that I'm comfortable with or that I understand or that I've experienced in the past. Okay? What's the number one rate that you guys experience or you're comfortable with, you understand? What's the units?
Miles per millisecond.
Miles per hour, right? Okay. So can I change this to miles per hour?
You can do whatever you want.
How do I get it to miles per hour?
You're gonna go, so how many miles in a, never mind. I do miles in feet, and then I would do like, how many seconds or
1
an
mile
hour.
over how many feet are in it?
Okay, so good. So here's the units I start with. Here are the units I want to get to. That's what I always do, okay? And I just start working with this first one here, and I try to get, obviously feet is not miles, so I want this feet to disappear. So I know it's got to be on the bottom, right? That's how they got to cancel. And now I ask myself, is there a relationship between those feet and the mile that I want to get to?
Yes.
Yes. Good, so 1 mile, 5,280 feet, right? In that case, the feet are going to cancel out. I'm left with only miles now up top.
Yep.
So I'm gonna be done trying to cancel that unit, right? That distance unit. I got seconds on the bottom, right?
Yep.
I want to get that canceled. Does anybody know how many seconds are in an hour?
360.
3,600. Okay. Now, if you didn't know that, let's do this. Do you know so if you don't know seconds to hours, you probably know seconds to another unit, don't you? Minutes. Does that make sense? How many seconds in a minute? Okay, so what would cancel here is the seconds, right? If I multiplied everything out, my answer would now be in miles per minute. Do you know how many minutes are in an hour? 60 minutes for every 1 hour. Now the minutes cancel out. Up top you're left with miles. On the bottom you're left with hours, right? Okay. Now, if I look at that right there, okay, these minutes would have canceled with those minutes, okay, and it shows you then that you have 3,600 seconds per 1 hour. Does that make sense?
Yes.
Okay. So if you want to use that fact, you can, but using smaller units of time might be more comfortable, okay? If I multiply those things out, that's what you get. I multiplied it last period. So 9 pi times 3,600, and then we had 5,280 on the bottom. This thing's traveling at 19.3 miles per hour.
That's low-key fast.
Okay. So that
For a kid, swinging
kind of
a
makes sense. Okay.
lot. Fast.
All right, so now let's talk about omega, which is the angular speed. Okay. This should be pretty easy to do. Angular speed's not a hard one to find. Theta we already figured out, right? Theta, remember, was revolutions times 2 pi. So we saw that to be 30 pi radians, right? What was the time interval that this was being done in?
10 seconds.
10 seconds. Okay, so I get, do any units cancel there? No, so I get 3 pi radian per second, right? Now here's my question. Can radians kind of maybe disappear? Because they're dimensionless, right?
Yeah.
If I let them go away, that second can't go away. Does that make sense? Okay, so I still have a per something, a per second. That unit is still there.
There's no feet in there.
So I can't just throw a random unit in there. So this is a situation where I said earlier, there will be a time where radians don't disappear in our answer. There you would leave radians in the numerator, right? Because it's by itself, okay? If it wasn't by itself, if there was a feet up there or some other unit up there, like there was in linear speed, we would have let the radian disappear. But this has to stay in this situation. Yes?
So do we leave rad in there whenever you deal with that strange W, or is it just...
Essentially, yes. Unless you're working with degrees, then it's going to be degrees per second. So all of this stuff, guys, we typically learn it, and a lot of our problems are provided with doing radian work. But there's nothing wrong with being able to do these with degrees, right? Okay, so if we're doing it with degrees, the only thing that changes is the 2 pi that we've been using to find theta ends up being 360. Okay. Now, let's see that this all pans out using V equals R times omega. What was R? What did that represent?
Radius.
Radius. So in this case, it's 3 feet, right?
Yeah.
What did we say omega was?
3 pi rad per second.
3 pi radians per 1 second. Okay, if I multiply that stuff out, what's 3 feet times 3 pi?
9 pi.
9 pi, and it'd be feet radians, right?
Feet rad.
What's on the bottom?
1 second.
1 second. What happens, because there's already a unit up here with radians, we can kind of wipe them away, right?
Yep. Wait, what?
Is that still my linear velocity?
Yeah.
Yeah. Done 2 different ways, kind of, right?
Yep.
Okay. So however you want to use it, it's up to you. You want to use R theta over T, or do you want to use R omega? That's fine. Regardless, usually these questions, guys, they're going to ask you both things. They're going to ask you linear speed and angular speed. So you're going to need to find omega anyways. So might as well use V equals R omega to find your linear speed. Yes?
So, is the next time we have a quiz or a test?
We'll have a quiz of this at some point.
Okay, are you going to give us these equations?
Yeah, early on I'll give these to you, and even on the like the tests and finals, because I don't want you to mess those formulas up because they are. I mean, they're very similar. They're not hard. I don't think they shouldn't be, but they, since the structures are kind of the same, S over T or theta over T, people transpose the S and the theta and put them in the wrong formula. So I don't want that to be an issue for you. So this is what happens on your car. Okay, let's talk about this real quick. So I think it's important to see some of the technology in which this stuff is used. Okay, if you were to take, now let me just see if I can get a picture here of one of these. All right, so you guys know what lug nuts are.
Yeah.
Okay, on your car. So let me just get a couple pictures up here because I know some people aren't maybe familiar with car stuff. Let's go. Rotors. All right, so on your car tire, okay, These nuts here are called lug nuts, right? They keep your tire on the car, correct? Okay. Now you see this little gray thing here in the back? This little gray circle. You guys know what that's called? Okay, that's called your rotor. Okay, which is one of these things. Okay. Now those are your brakes, essentially. Okay, because your rotor, you attach what's called a caliper to it. Okay, and let's see here. Well, let's talk about brake caliper. You attach one of these brake calipers like this to it, okay? And inside that brake caliper are hydraulic pistons that your brake fluid controls, and it squeezes that rotor. Does that make sense? Okay, so it creates friction, squeezes that rotor, and it makes your wheels stop. Is that okay with everybody? Okay, so that rotor is actually attached to this thing. Okay, this is called a wheel hub. Okay, that wheel hub right here, that circle right there, is where your axle comes through and attaches to your drivetrain. Okay, or your differential. These are the posts that your lug nuts screw onto and your rotor attaches to. Okay. Now all of these, especially in your newer cars, they're going to have, you see these wires coming off these, right? Okay. Those connect to your computer, your onboard computer in your car. Okay. It's your ABS and all that kind of stuff. But there are sensors that are inside that wheel hub. Okay. Because that thing's going to move around. Does that make sense? Okay. There are sensors in there. I'm just going to go back to this to draw just kind of a basic picture. There are sensors in there that will say, okay, every time that part of the wheel hub passes by that sensor, we're going to calculate the time that it takes to move one revolution around. Does that make sense? Okay. Now the radius of all these circles, okay, of your wheel hub and your bearings and all that kind of stuff, that radius is always constant, right? That doesn't change. Okay. But the speed or the rate in which that sensor or that marking comes back to that sensor will change. Okay? So what happens here is that through that technology there, okay, your car's computer is able to determine your linear speed by taking how fast that angle changes, the omega, okay, and then divided by the time that it took that mark to get back towards the sensor. Does that make sense, everybody? Yes. And then that is displayed on your dashboard to you as a speed. Okay? It's not, so what I'm trying to get you to understand is that the speed on your dashboard is not being found by taking the distance you've traveled divided by the time it takes you to travel. Okay? It's taking omega times t, or divided by t, omega times r, I said omega times r, of your wheel assembly. Okay? However, those two values are identical. Distance equals rate times time, or rate equals distance divided by time, and your linear speed are the same. Does that make sense? Okay. So when you see these questions about like taking a bicycle wheel or car wheel or something like that and asking how fast is this lady traveling, obviously your bikes probably aren't as advanced as your cars are and you don't have a bike that does this, but you could, count how many times your wheel is going around, okay? You ever put, like, when you were little, we used to put, like, baseball cards in our spokes of our bikes. And when you did a revolution and your baseball card hit the post of your bike, you knew your tire went around one time, right? Does that make sense? Okay? You guys ever ride bikes?
Yeah, but, like, we didn't count it like that. We made it sound like...
I know, you put more in there and that kind of stuff, but you only put one in there. Every time you heard audible noise, every time there was an audible noise, you knew one revolution. So you could easily count how many revolutions you're going through when you ride your bike. Okay, you can then take a stopwatch and determine then the time that it took to get to 125 revolutions. That will tell you then your speed that you're traveling.
You're a weird kid.
I didn't do that when I was a kid.
You act like you have so much knowledge about it. You act like...
All right, so a woman is riding a bicycle whose wheels are 26 inches in diameter. Those are, when you're doing these problems, that's where they catch a lot of people Do I ever need diameter?
Divided by 2.
Okay, so I need 13 inches here for my radius. Okay? It says the wheels rotate at 125 revolutions per minute. Okay? That right there tells me what theta is. Remember, theta is 2 pi times revolutions, right? So 2 pi times 125 equals 250 pi radians, correct? Does that make sense, everybody? We cool on that? All right. So let's find the speed in which this lady's traveling. Let's go omega first. It's theta divided by time. Okay? Theta was what?
2 pi times the number of revolutions.
Okay, so 250 pi radians, right? Here is where we get crossed up sometimes. In the last question, the time period was 10 seconds, right? What's the time period here? 1 minute. Okay? And they don't say 1 minute, right? They say RPMs, which is revolutions per minute. Revolutions per 1 minute is the kind of the understood phrasing there. Okay? So if I go 1 minute here, okay, what happens in this situation? We see that omega is the same value as our theta, right? And some people get crossed up because you'll see maybe 5 or 6 questions like this, and you'll say, my omega is the same thing as theta, and we always write that. But then the next question will say that they do it in 10 seconds, or they do it in 15 seconds, and then omega is not the same thing as theta. Does that make sense, everybody? Yes.
Why'd you multiply 125 by 2? Like, I understand.
Because you said 2 pi times the number of revolutions.
Okay, thank you.
So now if I want to find the linear speed is r times omega, right? What's r? 13 inches times omega, which was 250 pi radians per 1 minute, right? Okay, now I'm going to keep going because they want me to go miles per hour. So here's the thing, guys. Always do the work to find linear speed in omega in the units that are provided with the information. Once you have that, then answer the question about putting it in miles per hour. So what do I need to multiply by? The radians are going to go away. The radians are dimensionless, so they're canceled. How do I get these inches to go away?
Inches up top, inches on bottom, I meant. Feet up top.
So that, right? So now inches go away. How do I get to miles then?
Feet in miles.
Feet on the bottom, miles on top, right? Okay. So now the feet cancel out, and I'm in the right unit for miles, right? So I'm done with those. Now I'm going to try to cancel out minutes. How do I cancel out minutes?
16 seconds.
Minutes on top. I want to get to miles per hour.
Minutes in an hour.
An hour on the bottom. So 60 over 1, right? So then that minute cancel out. If I multiply straight across, I get 13 times 250 pi times 60. The units will be miles. And then 1 times 12 times 5280 on the bottom. And it'll leave me hours. And that will then, once I calculate that, that will tell you the speed that this lady is traveling in miles per hour. Okay. Chuck, the homework, 5-1, day 2. And actually both of them. 5-1, day 1. Let's make that due Tuesday. It will cancel off Tuesday night. Okay.
What about the other one?
The other one Wednesday.
No time to do it.
Okay. You have no time. I'm giving you 3 days off plus Monday and Tuesday.
Who was the one person in like Miss Hook or Miss Lawnick's class? This is the only reason I remember it. Is we were in math together, and it was either I think Elijah or like me, and they were like, "Yeah, well, I remember 5,000 miles and all that mile," and because he was like 5,280.